run into problems. So hello, hello, Kevin Asiago, can you confirm that this is where we left last time? What was the last topic we covered? Now, are there people on the other? Please, can you respond so that we move on? Amos, Nikki. Kevin. Kevin Asiago. What was the last topic we covered? Hello? Anyway, it's up to you. So the geology plays an important role in many of these decisions in designing and constructing a tunnel, from determining its feasibility and the cost uh, to assessing its performance. In tunnels, unlike other projects, other structures, the ground acts not only as the loading mechanism but also as the primary supporting medium. So if this is uh, the ground and then you do your tunnel here, if that is your tunnel, and so you can see there is a height here, height of overburden, and if there are structures here, if there are houses or whatever kind of structure they are, all manner of structures, houses or whatever, they all add up to to load the tunnel, while at the same time the length of the strength is provided by the soil. So the rock is the strength, is what provides the strength, and this very rock is partly loads forms part of the loading on the tunnel. So in tunnels we usually have something we call the EDZ, the excavation damage zone. So there are some solutions. I think that's beyond the scope of this class, but I try my best to explain. Because of the first of all, if you understand your soil or the principles of soil mechanics. So if this is your, please make sure you can see what I'm doing. So if there is no excavation, for example, or maybe I explain here, it would be easier to see. or maybe let me insert an empty an empty yeah, let me insert an empty slide so that probably what I'm saying is clear. So if this is your ground, for example, please mute yourself. Someone is who is this? Asiago, Kevin, mute yourself. Mute yourself. If you continue to make noise, I will drop you off the class. So there is a sigma v. You should know yours already. There is a sigma h, and there is some ratio of k. For at rest pressure we call it k naught, which is sigma h over sigma v over sigma prime v. Now that's the state. So we can say this state is at rest. Everything is balanced. But now when you come and create your tunnel, so you unload. All right. So when you're there, the element here, for example, the element that was here, because of you have unloaded, you have removed some. So this value, so let's say sigma v1 and sigma h2. So these values are different because of, and the k here is now different. So k, let's call it k01, because of readjustment of stresses around the hole, because you have created some let's say some not necessarily vacuum, but let's say vacuum in quotes, because you have created a void. So there is an imbalance, and the stresses readjust. In fact, there is what you call a cast solution. I think if you want to study more of this, you have to study, excuse me, you have to study a higher degree. So there's what you call a cast solution that is used to get or to calculate the stress readjustment. So if this is a hole, then if you draw a curve so this hole has some radius, let's say is a. So the EDZ, because of the readjustment, the stress the cracking will happen based on the distance from the center. So let's say some radius, some radius which is above the hole. So if you draw a curve of r over a to what you call, because this hole has some, there are forces, let's say, maybe from here. It's easier to indicate, let's say this way, let's say. So there are stresses in this direction are called sigma r, and again, similarly, there are stresses tangential to the hole are called sigma theta. And they are what we call the principal stresses in this element or in the soil. There are principal stresses which are sigma 1 and sigma 3, as you know. So this would be probably sigma 1. If you remember your Mohr circle, sigma 3. So, but in this context, these are usually called P1 and P2 from the analysis of the KISS solution. So, if you are to plot the graph of sigma, the stress readjustment, sigma theta over P2, at this point, this point is usually called, we call it the side wall, uh, the side wall, or we can call it the spring line, the spring line. So this curve is goes something like this. Um, for different values of k, in fact. Okay, this is, let me just show you this one curve. So for different values of k, that's what the curve is. And for this is a value of around 1. So from the, actually, in fact, from the analytical solution or from the key solution, we are always interested in what you call EDZ. EDZ is called the excavation damage zone. Excavation damaged zone, damaged zone, or EIZ, the same thing, excavation influence zone. So we usually are interested in this. So at the spring line, this is the solution. At the spring line, that's the solution. Now at the, this is at the top, we call this the crown. And here, this is called the invert at the bottom. So the solution at the crown or at the invert are a little different. I unfortunately I have to. Okay, maybe I create another. The solution at the, okay, maybe I draw here. The solution at the at the the solution at the bottom here. The solution at the spring line. The spring line, the definition is either here or there. And this is, for this is the invert, and that's the crown. So at the at the crown or invert, the solution is something like this. So R over A, you remember R over A is so A is the radius of the circle. but r is any radius from the center of the circle. So r over a, and you draw sigma theta over p2, depending on the various values of k. In fact, some of them are negative. I think starts from -2, -1, and 3, 5 to 8. Anyway, that's beside the point. So these are for different values of k. So these curves will approach a value of 1 here. This is how the curves this is how the curves this is the solution to the curves. I think to make much better sense, let me show you I think part of this from my thesis, just to highlight the point. So let me stop sharing this, okay, and then I will share with you. So I think it will make more sense. um, yeah, okay. So this is what I'm trying to explain. The Yeah, so this is what you call the Kist solution. These are some equations for. So if you're interested, of course, this is beyond the scope, but so that you have an idea, this is the assumption that is made. So when we have a hole here, the radius is RA, and if you want to find any stress any from any distance from the center, so we call it R, and this is the you can see sigma theta is tangential to the circle, and sigma r and tau r. So and then this is called P1 and P2. Remember, yeah, the what I have explained in the slide. And these are the equations how to calculate the sigma r, how to calculate sigma r here, and sigma theta here. This is how to calculate sigma theta and tau r. So this is how to calculate the stresses. And the solution, I think what I wanted to explain most importantly. So at the crown or the invert, these are how the curves go, and we are interested in the r over a. So for we can say here the value of, not this value is important, r over a is 2, not 1. Sorry, I think I misrepresented. So this is 2 for this case, and for different values of k, I'll explain what those means. So k is 0, k is 1, 2, 3. So 3, 2, okay, 3, sorry, 0, 1, 2, 3. So these are the curves. And for the invert, you can see for k is 0, 1, 2, 3. So that's the stress redistribution. I needed you to see the curves and the stress redistribution. The formulas are beyond the scope of this class. So the point there is that yeah. So the point here is that yeah. So sorry. So this is not. So this is not one. That's two. This is two. So it means the physical meaning is that at this point in this area there is high stress readjustment due to the unloading, and therefore this, for all intents and purposes, this can be called the excavation damage zone. When R over A is 2, what does that mean? Anyone who can simply say what that means? If uh, anyone, if R over A is 2, that means what? That 2A, R, in fact, R is 2A. What does that mean in practical terms, where A is the radius of the tunnel or of the opening? Hello? Class rep? Class rep? What does this mean? I hope you have been around. So you think it's a good thing you are just joining class now? Hmm? Hmm. Okay, so anyway, so it means that for the from the analytical solution always assumes that the EDZ uh, is within the diameter of the hole. So if you do if you do if your tunnel is of a diameter d, then the assumption is that the influence zone, the excavation influence zone, is also of the same diameter. As you can see from this solution, is that so while we are here, it appears that the stress readjustments, there is no change. There is no the changes in the drastic changes in stress redistribution have stopped. So for all intents and purposes, that can be described as the excavation damage zone. However, the assumptions of these formulas are based on a very good rock, homogeneous rock, uh, uh, class 1, like a very good rock, so to speak. We assume linear elastic. So uh, unfortunately, in reality, the solutions do not agree with what the observations or what people see in practice. So this is one thing, but at least the solution, the KISS solution, gives us a way to understand the stress redistribution around the tunnel. So the ground acts not only as the loading mechanism but also as primary supporting medium as well. When the excavation is made, the strength of the ground keeps the hole open until supports are installed. Even after the supports are in place, the ground provides substantial percentage of load carrying capacity. That's for tunnel designer and builder, the rock or soil. So, in a nutshell, the in tunneling, the rock or the material in which tunneling is done carries most of the loads. Uh, Sometimes we provide support. For example, we do lining inside. Lining is some concrete, semicircular concrete structures that can be installed around the tunnel like this. And these ones are because the drilling action may not be as aesthetically pleasing to the eye. So because people will be driving through and you must make it look nice, to look smooth. So we install linings which the plumbers can now make it look very good and very nice. Okay, this is one function of the liner, but again, liners can support if, for example, the strength is not enough. The liners, we'll see how to design liners later in this course. Liners can provide enough strength to support the opening, but still most of the forces are carried by the rock itself. So surrounding a tunnel is a construction material, in fact the rock or the soil surrounding a tunnel is the construction material in fact. So its engineering characteristics are important as of those concrete or steel used in other aspects of work. Because every project is unique, in this chapter we set forth some broad guidelines and overall perspective or approach. So this is not a cookbook, this is a point. We just want to equip you with the knowledge and the skill. Remember the what we've talked about, we said about the key solution. The solution it looks quite good, but in fact, it doesn't agree with what is seen in practice. But also need to understand because the assumptions used to derive the formula are based on homogeneous rock, grade 1, now very strong rock. But in reality, this is often not the case. So, and this is why we are saying this is not a cookbook. We are not, this, what we are teaching you is not, you're going to take it and apply for every project. You must, once you understand the knowledge, you must assess every project on its own merit. So this chapter concentrates primarily on the geotechnical issues and investigative methods that are important in tunneling. It is the anticipated problem that can create costly delays and disputes during the tunnel construction. It has been shown that the more thoroughly investigated tunnels have fewer cost overruns and fewer disputes. Like I said, because these projects are quite expensive, in fact, so it's better to get it right the first time. Otherwise, there is danger of running in cost overruns. In fact, if it is ill done, the people have run, because if you realize you are already in implementing the project and realize it's not feasible, you may have to abandon. and you have invested billions, if not trillions of money or dollars or shillings, then people have gone bankrupt. So the explorations help to evaluate the feasibility, safety, design, and economics of a tunnel project by developing sufficient understanding of regional geology and hydrology for project design and construction, defining the physical characteristics of the projects that will govern the behavior of tunnel, uh, help uh, helping define the feasibility of the project and alerting the engineer and contractor to conditions that may arise during constructions. So, for example, the usually underground water is an important element of this part of construction, and of course, the presence of water makes everything a little bit more complicated. So, uh, you need to know that you'll encounter water than starting excavation, and then you encounter water in the process of construction, and this in fact has led actually to loss of lives in other places when things that were not anticipated occur when under construction. In fact, tunnels have collapsed, people have died, and these things happen because of unforeseen circumstances. There are some factors that probably the geotechnical investigation was either not properly done, or not enough information was collected. So, providing data for selecting alternative excavation and support methods, and where project status permits, determine the most economical alignment and depth. In fact, there are different methods of construction and excavation. We shall talk about them in detail. So, depending on the ground condition, when there is water, when there is no water, you choose a certain type of excavation, and when there is water. So, all these factors affect the different. So, you need to do a geotechnical site investigation to decide on the most appropriate method. When there is water, of certain methods may not be used. So providing specific rock, soil, and hydrologic design parameters, minimizing uncertainty of physical conditions for the bidder, predicting how the ground and groundwater will behave when excavated, and supporting by various methods. Again, you realize that you are doing an excavation in you are doing an excavation you are doing an excavation. That guy is late. Someone wants to log in. He's late. Let them wait. uh, what did I want to say? Predicting how, yes, because you already, this is your tunnel, for example. I don't know, let me use red. So this is your tunnel, for example, and there are people's buildings there. Maybe there is a mall, there's some high-rise building there. Those are people's properties, and you're digging a tunnel. When you're digging a tunnel here, of course, the tendency of the ground would be to settle under the, all right? So you must take care of all these things, because once you do this and these buildings are affected, or whatever property there is, you will be sued. You'll be taken to court, and probably pay a lot of money. So all these things you need to think about them, because the activity that you're doing is going to affect it will affect your will affect you. Also have to think of how these activities affect other people, because you are not working in isolation. Establishing a definitive design condition or geotechnical basis for the bid, so a change condition can fairly be determined or administered. So, for example, when okay, contracts can be varied because, if, for example, if the certain conditions have been met, or have been you've encountered certain conditions that were not could not be reasonably foreseen, and then you bid for a certain amount of money, and obviously these projects are expensive. So if the condition experience is substantially different from what was anticipated, then you may need to vary even the contract sum and amount. And of course, you need a fair way to do this. Even at the time of bidding, you need a fair way to determine the what the cost of the project is, depending on the complexity or lack of it. During construction, so improving the safety of the work, of course, the primary thing is for safety. So when project funds permit, providing experience working with specific ground at the project site through large-scale tests or test exploration, which in turn will improve the quality of design and field decisions made during construction. You also provide specific data needed to support preparation of cost, productivity, and schedule estimates for design decisions. So when you do the site investigation, you have data to back up. If you say, for example, we will the excavation, for example, will be this much. The excavation is in hard ground, in soft ground. Because you have done the investigation, you have the primary data to support your position. So there is a world of difference between geotechnical requirements for underground projects and those of surface. I think this cannot be overemphasized. And I will say this again: the experience is important. It's not only important the knowledge, but the experience, because you may have the knowledge, but the experience is important. And in fact, this is why in such projects you will find a group, battery, in fact, of engineers, everyone bringing a unique experience to reinforce each other, so that the project is carried out safely. So you find a long list of engineers, each have a different experience. For example, in a tunnel, you need structural engineers, of course. You need geotechnical engineers fundamentally. Even the geotechnical engineers have different specialties. There are people who specialize in rock, others specialize in soil, others specialize in rock structure interaction. So in this kind of project, you find each person, each bring their own unique experience, which is important because every element is important to make sure the project is safely delivered. So not only are underground projects geotechnically intensive, but the nature of the ground changes both horizontally and vertically. I think that's uh, the point. In fact, that if this is your ground, As you go down, there is some variation. Again, as you go horizontally, there's variation in terms of probably permeability, variation in terms of stratification. The soil may be stratified or this way, or may be stratified. So the point is there are a lot of variables that you need to think about. So the type of excavation method and support that is used also affect ground behavior. Even the quality and timing of the construction affects how the soil or rock behaves. So, uh, actually, once you, I think I said this already. It bears repeating that. Uh, so, in this is the balance condition. So once you do the excavation and there's an opening there, once you do the excavation and there's an opening there, the ground, there's what we call a ground reaction curve that determines when because uh, ground reaction curve, this determines when the ground is stable, because when the stress readjustment will take some time. The once you do the unloading, you remove the when during the excavation, the ground needs time to react to the changes in stress, and so all this. So this is why we say the timing has some effect. So every geotechnical program must predict ground behavior so that it can be translated into the selection of construction methods and support systems, and that the estimation of costs, the determination of stratigraphy, and the elevation of groundwater table alone are no longer sufficient for an underground project. Rather, these descriptions are just the beginning of what is needed from the investigation programs. The geotechnical challenges of the uh, underground work, the underground poses some formidable but not impossible challenges to geotechnical and tunnel design teams. Some of these challenges are that there is a vast uncertainty in all underground projects. The cost and feasibility of the project is dominated by geology. In fact, we in this course we are going to spend some time to describe how to classify the rocks, so that you can know this is a good rock, this is a poor rock, this is a very good rock, this is a fair rock, and so on. So these kind of descriptions will let the tunnel engineer or geotechnical engineer have an idea of the nature of the rock or soil, basically soil, not soil, sorry, rock, that they'll be working in. Like we've said, the primary support structure of a tunneling is the rock in which it is built. So the primary material. So we need to take care of this material and make sure that this material is able to support the tunnel. So every feature of geologic investigation is more demanding than the traditional foundation engineering projects. The regional geology must be known. Okay. So engineering properties change with a wide variety of conditions such as time, season, rate, and direction of loading, etc. Some of them change drastically. In addition to a lot of uncertainty, in fact, even in subsurface, even for ordinary projects like buildings or just foundation, a traditional foundation of there's a lot of certainty. In fact, now when you are working underground, there is more. The level of uncertainty is compounded. So groundwater is the most difficult condition parameter to predict and the most troublesome during construction. Even comprehensive exploration programs recover relatively minuscule drill core volume, less than 0.005 to 10 minus 4% of the excavated volume of channel. So even if you are very careful, you say you want to do a drilling program to get a very good uh, preliminary result upon which to base your designs, the best you can do, uh, in fact, is to recover this percentage of excuse me, of what you will need to what you will need to excavate for the entire tunnel. So it is actually guaranteed that the actual stratigraphy, groundwater flow, and behavior encountered during construction will be compared with geotechnical team's predictions. So it's good to do the investigations and then have an idea of what are the expectations. The civil engineer works with man-made materials that are subjected to frequent inspections and tests. So in a concrete structure such as tunnel lining, one cylinder is frequently taken and tested in the order of every 20 yard cubed volumetric sample to production ratio of 1 to 2700, and the slump and consistency are least visually observed continuously. The geology to be tunneled is, however, never seen at full scale. Anyway, the point here is that for things like concrete, you can have an active way to assess the quality and in a fairly consistent way. Because if in doubt, you just take the sample, you do the testing, the slump test, or whatever kind of testing you need. You can even ascertain the compressive or tensile strength if you want. But for a tunnel, by the virtue of the fact that it's underground, you cannot recover very little samples to test. Beyond that, in situ, there are a lot of uncertainties. So you never see it at full scale. You can only use models to try to predict the behavior. So in fact, the ground is never exposed fully. So until then, it is evaluated by observation of extremely infrequent samples. I have said this, and even fewer tests. So because you cannot see everything at once, you will go and pick certain samples which do not well give us useful insights. However, are not a significant percentage of of uh, the actual condition. So, for instance, if borings are drilled in 300 feet centers and continuously sampled through the tunnel horizon, the amount of material recovered would only be in order of 0.05% of the tunnel volume of the tunnel volume. So interpretations is complicated because the characteristic of the soil or rock frequently change both horizontally and vertically every feet. So these factors listed in the table shown alongside the field, crucial to the field to prediction of the field behavior from laboratory oil field tests and demonstrate the complexity and uncertainty of geological data. So in fact the other part is that, for example, for soil, the uh, you can take a sample and uh, the sample may very well represent the actual in situ conditions. Now, for rock, while you can take a sample to the lab, there is what is called scale effect. That's the first thing. The rock, uh, the rock, the property of intact rock is substantially different from the rock mass because uh, the rock mass may have other, like for example, may have discontinuities, may have some fractures, some cracks. Now, when you sample, you just sample. It's possible to sample a portion that do not have the cracks or do not have the fracture. So when you only use this to characterize your the rock mass, then you'll be overestimating the strength because in fact the actual sample may have other discontinuities. So in the table there shows you the complexity of the difference between the lab test and the field. In fact, sometimes the strength behavior may vary even with seasons. So I think we can take 5 minute break. We class rep, we can take 5 minute break and then proceed, or 10 minutes break. I think we resume by 11:10. Please continue to register your presence by writing your name and number. I see people writing like Nyendo, Manan, and Mercy. Can you just write each individually because this is not one person. The number shown there is just for one person. Write you each person to write their own number and their own name. Okay, we'll resume at 10 minutes past. Okay, please confirm you can hear me and we proceed. Hello? Hello? Class rep. Okay, so the importance of geology. The geology affects every. Okay, I think this one we've talked about. Uh, So geology affects every major decision that must be made in designing and constructing a tunnel, determining its cost and to a degree even the performance of the final product. The one-to-one relationship between geology and cost is so dominant that all parties involved in the planning and design of tunnels must consider geology and hydrology of the site. Decisions such as general alignment and depth affect host of decisions and issues because they may place the tunnel in or out of adverse geological feature. You remember when we talked about the factors that determine the route of a tunnel. So because again, if I believe you have done it's called what, geometrical design of roads, the issues of super elevation, the concavity, the super elevation at corners to ensure that drivers do not veer off the road. You have to do a certain radius. This is the same idea with the tunnels. In fact, you remember one of the factors that affect the construction is that you need to consider that the TBM, the tunnel boring machine, can negotiate corners. So because of these alignment requirements, basically for safety, then you might find yourself that the route is heading towards maybe a hazardous material, or maybe a place where there's a fault, or maybe a place, maybe a lava, a place prone to volcanic activity, things like this. So then the geology is very important because again, the proper alignment to ensure safety has to be maintained. So all these things go back to the geological makeup of the rock. So this not only determines construction cost, it can affect long-term maintenance problems such as groundwater leakage. For this reason, the early exploration is made, the greater the potential for savings. So again, the issue of groundwater need to be carefully considered because if, for example, the tunnel is gonna be used to put up electric trains, the paths for electric trains outside the subsurface, the outside the surface, you could use the trains. The electric trains I don't know. Maybe I'm saying things that I need to know that we are saying the same things. But the electric trains use electricity outside. If you're talking about in an open space, the electric lines are within the same lines of the railway track, and there is a way that they tap electricity, and the slipper, is it called slipper? There's some mechanism that electric train uses to tap electricity, and this mechanism is always attached to the line for the entire length of the length of the track of the railway. So this mechanism attaches itself to so that the electric train can always get good supply of electricity. So for example, if the electric track was from say Mombasa to Kisumu, and that's a distance I think of 800 to 1,000 kilometers, for example. So the entire length from Mombasa to Kisumu has electricity, and then there is a mechanism through which the electric train is attached to the line, so that all the way from Kisumu from Mombasa to Kisumu, it can always get supply of electricity. But you see, that requires a lot of space, because then the place where to put the electric lines and so on. So you need a lot of space because the electric lines are kind of tall. Now, inside a confined space like tunnel, if you would have such structures, then it means the height of the tunnel would be very large. Again, that has to do with the construction. That would make the construction even more complicated. You need more space. You need to carry more loads. Need more support. So that would make it more complicated. So then, what is normally done is the electric lines are laid on the track. In other words, they're on the ground. So the reason I am saying this is to bring out the issue of groundwater. So imagine if electricity is on the track, because the railway track, and at the same time water is leaking. You can see the hazard to people, because these the tunnels, it will serve people. People will go down there to get into the railway, the tracks, the mass rapid transit, if it is the mass rapid transit, to commute from one place to another. So you can imagine water and electricity. So then you need to be aware of the water, and if you need to seal off the water, for example, if we are going to use electric trains that have electric supply on the tracks rather than hanging overhead. So this is important. Again, the kind of material, if you have good rock, probably the cost wouldn't be much, because most of the loads can be carried by the rock. But as if you have poor rock or soil, you need a lot of support. You need special skills, special ways to do the boring, the tunneling itself. So the cost, again, the resident rock or the host rock, again, is a key factor in determining the cost. So all these things you need to know in advance, so that you can save. And so the regional geology must be understood as fully as the specific geology within tunnel corridor. In some cases, it may even be desirable to conduct explorations, including borings well off the site, to gain an understanding of the overall geologic and hydrologic picture. This might aid in determining the regional strike and dip of the particular geologic feature. Again, some factor that affects the behavior of rock is what you call orientation. Has something to do with the dip and strike. These things have something to do with the stratification. So I have to. Yeah, so for example, if this is your, sorry, I'm looking for a pen. So if this is your rock, and then there is some form of certification. So the strikes and the dip have something to do with these orientations of these angles. That's what we are saying. So these things affect the overall behavior of the rock. In fact, if it were left to us, you wouldn't like a rock with this kind of orientation. But in fact, in reality, this is what, because this form from natural processes, the folding, faulting, affected by volcanicity and so on and so forth. So you can meet all manner of ground conditions, and more often than not we encounter stratification, we encounter rock that have strikes and dips, as already explained. So all these and these things affect the strength, and as a tunnel engineer, you have to be aware and have mitigative ideas. Also, the issue of the presence of water is important as well, as I've explained. This might aid in determining the regional strike and dip of the particular geologic feature, or explain a complex groundwater regime, which in turn could be extrapolated into the project area. Such exploration can also help determine whether a certain adverse feature is local or pervasive. For example, uh, for example, say you have stratification, like I've said, and then there is a some layer of rock, for example, and first you need to make sure that the rock is continuous or not. But besides the point, so if there is a thin layer of weak rock here, for example, so maybe limestone, let me say, limestone, and this is rock. So uh, if you detect some things like this, you need to know whether they are just they are existing in a wide area, or so this is what we mean by local or pervasive. It's just isolated, or it's called ubiquitous. It exists everywhere. Ubiquitous. So you need to to ascertain all this, because it's important. Geology provides crucial insight into third dimension, which is frequently overlooked, especially on root type projects. So it's important, and you need to also consider the other, for example, these natural phenomena, like if there is a fault, if the place is full of magma or lava, is prone to earthquake activities, and so on forth. So this is important. Also, you need to consider. Hopefully, it may not happen. The You need to keep off hazardous material, like for example, the in some countries, the nuclear waste repository. In fact, in most of the developed world, uh, the 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 short-term nuclear waste are deposited inside a rock. Long short-term, the low risk, I would say, low risk, short-term. These are nuclear waste that have are low risk, like they have their half-life. They are almost at the end of their half-life, almost, because actually it's very difficult to know the exact the half-life, but the risk of these wastes are low, and so some governments can allow that they can be deposited inside the rock Hopefully, with the time they will reach their stable isotopes. But that's besides the points. But so far, no, I think no country in the world has authorized the use of nuclear of repository of rock, in fact, or geology as a repository for long-term high-risk nuclear waste. So this you need to get this clear, because the long-term nuclear waste are quite pose a danger. In fact, those who listen to the issue between the war of between Russia and Ukraine, you can see that every time there is an issue around nuclear, the UN is up in arms. Other countries are saying this is dangerous, because we all understand the potential danger that nuclear poses to, in fact, human existence. You can read the history of the nuclear issues in Japan, the nuclear strike, and I think there was also nuclear leakage. Is it in Italy or Spain? Some country in Europe, and in fact, these days, is it? It's only people after so many years. It's only people trying to to repopulate the place, because after the nuclear strike, the place was deserted. I think for a number of years now. So this is the danger. So far, so this is why I'm saying the long-term nuclear waste cannot be deposited in active rock. But for the low nuclear waste, some governments can allow, because the risk posed by such waste would not are not m- are not are low. Now again, but so even though the risks are low, when you're tunneling, you do not want your tunnel to go through such places. So you need to keep off the hazards. But again, you should remember that the direction or the route is determined by the designed alignments that have to follow certain curves or certain rules of certain radius. So if for example your the design uh, ensures the safety design, the radius or the alignment makes the tunnel to pass through uh, some hazard, then of course the design team has to rethink to make sure that the hazardous place is avoided. Of course, certain times it's impossible to. For example, if uh, if you have a fault, for example, in Kenya, there's a Rift Valley. I think there are potentials of faults there, and then the route has to pass through, because if you are doing a tunnel, for example, from Nairobi to Kisumu, or from like to link the western to the western part to the eastern part, the only way is that that tunnel has to pass through the Rift Valley, must pass through where the fault is. So, uh, so in such a case, the design team must look for the least, the uh, even if it has to pass through the fault first, enough design measures have to be taken to ensure that if disaster strikes, if the faulting occurs, then the tunnel is saved. All right, or if this happens, then there is least casualty, the danger posed by this when a casualty occurs would be least. So they would choose a position where if something happens, then the casualty would be least impactful to people's lives. Because in fact, sometimes it's impossible to keep off these hazards as well. Of course, for nuclear repository, those ones you can keep off, but for natural phenomena like the fault lines, sometimes you have no choice. So geotechnical conditions and geotechnical conditions are usually presented as cross sections or profiles, which are usually two-dimensional representation of some idealized profile obtained by projecting of alignment, boring data, and or outcropping formation to the plane of alignment. Naturally, geology varies in all three dimensions. In three dimensions, this because in the Z, also in the X, also in the Y. So everything changes. So you have a lot of variables. This is a point, and we cannot stress this that a lot of investigation and data need to be obtained to justify the decisions. So the uh, and a knowledge of regional and local geology can allow one to estimate how geology varies not only along the alignment but perpendicular to it as well. This knowledge gives valuable insight to the relative location of adverse geological features, the extent to which the tunnel might be affected by them, and the likelihood that a different alignment may be better. So this exactly what I was saying, that if from the investigation and then you realize that the point through which the initial alignment uh, were to pass has some issues, some challenges, then once with this armed with this knowledge, then probably you might find a less hazardous area or a different alignment that is safe. Geology also plays an important role in evaluating geotechnical conditions between borings. Significant changes can occur between adjacent borings, which initially are typically spaced at 500 to 1000 feet, and it is important to use geology to interpolate between widely spaced borings to predict how long the tunnel will be in any one given ground condition. In addition to the ground levels and existence of perched or artisan water, a study of the hydrology of the area can provide information about the flow patterns of groundwater. So again, you need to be aware groundwater is important, the patterns of flow, if there are wells, the artisan well or not. There could be also like just patches of water rather than continuous running water. You need to be aware. This is of particular interest when hazardous waste is encountered. I think I've already said this often. Again, this is important when hazardous waste is encountered or when trying to determine groundwater condition behavior. For example, the waste, the nuclear waste I was just talking about before. Again, if there is a water floor and the rock is compromised, the integrity of the rock is compromised, and probably the water is washing away radioactive material. You need to be aware, and because at the end of the day, all these things a lot of money is invested to make sure there is safety, and as you as well as an engineer is take a lot of time in training, spending a lot of money as well to make sure you have the right skills. So at the center of all this is safety of the projects that we are going to implement. So geology also provides clues to problems that may be encountered when the tunnel is constructed. For example, deposits of glacial till frequently have boulders associated with them. Accordingly, boulders should be expected even if the actual boring did not appear to encounter boulders. Geology can also provide some insight to as to how certain materials will behave during construction. For example, there is there is some uh, There's some project there in Seattle, I think, in the U.S. It was known from previous construction in Lawton clay that it could be expected to be fissured and slickened sided pervasively, thus changing the soil mass properties from that of the an otherwise very hard clay. So again, previous experience is important. So if, for example, a tunnel had been done in the area that you're currently doing a tunnel, it's good to look at the previous data, and it will give you good insights so you can avoid potential issues. So thus geology provides rationale means of correlating particular tunneling conditions, types of ground, and case histories. It can provide a menu of potential problems as well as their solutions, and a means of for predicting tunnel behavior in similar geologic materials. This can be very beneficial to the owner if it is done during the initial segment of major undertaking, such as subway system that will be developed in stages. So, so far, if there's a question, you can ask. Class rep, anyone with a question can ask. No questions. So no question. Okay, so we talk about the facing and timing need for geotechnical services throughout the project. So first of all, the after the project implemented, again we need to see the lifetime, the what you can call the service, the behavior in service as well, so that we make sure that it serves the purpose for which it was designed. That's the first thing, and also that it's safer in the long term. And if there are mistakes or things that can be improved, and this in the long term, in fact, helps in developing data. just a minute. Yeah, so you need to maintain the project throughout its lifetime, collect data as well to see whether the project is serving the purpose for which it was designed or not. So after construction, to the document as built behavior of the tunnel as shown. So there's a table here. I also have to explain this is not a good way to. These tables I have gotten from a reference, and renumbering them would make me is would be is would take some time. So I just copied table 2. But for your writing, you'll do a project. This is not, you cannot start numbering a table from 4.2 as you can see. So you have to number sequentially from 1, 2, 3, and so on and so forth. So for this case, this is just applicable because I copied. And when I refer to it as 4.2, it's easier because otherwise then it means I have to renumber uh, the the tables that I'm going to use in this note, and it's likely that if you don't check correctly, it's easier to make a mistake. So I think I hope that is clear. So naturally, the level of geotechnical services provided will change throughout the life of the project. For instance, the geotechnical services might be limited at first to the collection of available geological data, then increase in level to the collection and evaluation of existing geotechnical engineering data. The level of effort may then cease temporarily while planning and financial decisions are made. Subsequently, a significant geotechnical work will be necessary during exploration, analysis, geotechnical design during the early portions of preliminary and final design, inters, inters, interspersed with relatively low levels of effort. Finally, during the later stages of final design. So this is just saying the how much effort you need. For example, when during the design you expected to go out, do some planning. So at that time, you might be okay. You might go just do limited geotechnical work. Probably you need to know where the site is, the direction, the survey data, the alignment, roughly where that's gonna be. So with limited technical input. Now, once you have this information, you go and then you plan. So during the time, the effort there's not very much effort because you're just doing the soft part, the planning. The financial decisions are made. Then once you mobilize, you need to do a drilling plan. You need to do audits. You need to do they're called pits, exploration pits. You then when you go on site now, active geotechnical work increases significantly. All right, because then you need to collect data, do the borehole loggings, you know, and then again once you get the data, it's taken to the laboratory. So during that time, maybe there's not so much effort because maybe the effort is in the lab. Again, once you get the data, so during the period through which the testing is done, probably not much activity. And after now you get the data for design, again the geotechnical work increases. Now this is the table for that shows you the level of geotechnical input. And this is important even for you students, because of course, the reason why you study this is a career subject for you. So when you get out there, we expect you to be writing reports. You make money because this is partly why. So you need to be aware of all these things, and I don't know how much time we have, but again, how to write reports. I think maybe not this class. The I'll show you some of the reports you write. So once you get this knowledge and you go out there and your license, again the other issue to make money. So you need to also know how to write the report. So this is why all this. So the when I don't know what I was saying previously. So when contract documents are finalized, there will be relatively significant geotechnical effort to support the preparation of the geotechnical design summary report, of course, and the rest of the contract documents. A genuine need for geotechnical input extends to the bidding, construction, and post-construction phases. Many projects are doomed at the outset, and I think I've said this before, because owners and some engineers who are inexperienced in underground projects do not understand the vital importance of geotechnical service to underground projects. In fact, I think this is not even underground projects. It's not limited to underground projects per se. In fact, even in Kenya, so far, I'm sure you're aware, you hear buildings collapse left, right, and center because people underestimate the value of geotechnical engineering investigations. In fact, from my own personal experience, clients come and they think if you give them, in fact, the if a typical geotechnical survey for maybe a 10-story building could go up to 1.53 million. But if for example, you ask them this, they think that it's optional, and also they think that it's expensive. But so you ask a person, for example, 8, 10 story, how much? More than 50 or 100 million, that range. So if for example you do the structure and it collapses, you lose the 100 million, and then you can spend 1 or 2 or 3 million to secure. You can see. So people underestimate the importance of geotechnical engineering. Actually, not even only in tunnel engineering, but also, in fact, I think for the case of Kenya, an unfortunate case. So sometimes you get clients, and then you tell they need you to do a thorough investigation, but the amount they are trying uh, to 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 the cost, the amount they are willing to pay is nothing. So it's a big challenge for us sometimes as an engineer, because again you need to take the money if they're offering. So you tailor the report. Not This is not to say you do a shoddy job. Whatever the amount of money they can offer, and if unless it cannot work at all, then you don't take the money. You just ask them to uh, you just ask them to do the right thing, or increase or get money that can do something. But if the money they are willing to offer can do something, you write, give them a report within the confines of what you're able to do. And then maybe if in fact if further studies are necessary, because of the amount he was willing to pay does not allow you to say a lot. So you tell him the report, okay, this I'd recommend further investigation. So sometimes you write a report and then they come back and say, so many is a big issue, in fact, but the thing is the people undermine the geotechnical services, which is important. And in fact, Kenyans should, in Kenya, people should take notice, because you can see buildings collapse. Because you can see buildings collapse willy-nilly. and it's a big issue in this country. So someone is asking that, is hard rock the good rock for tunneling, or is it expensive? I think that's a question that is not simply answered the way Kevin. That question is not as simple as you put it, but we will see that the rock, it doesn't have to be hard. There are certain aspects. For example, if has an orientation, that's the first thing. Either they are discontinuities, the strength from tests, uniaxial strength or other tests, you know, the discontinuities, whether the joints are rough. So once you check all these things, and then you're able to give some marks. We'll see, I think, in the next topic. Then you can give marks and say, okay, this one, in fact, there is a rating system that gives marks for rocks between, I think, 0 to 40, I believe. 0 to 40, that's a poor rock. No, 0 to 20 is very poor rock. 21 to 40 is poor rock. 41 to 60 is fair rock. I think 61 to 80 is good rock, and 81 to 100 is. So you score the rock as if like the way we score your grades. And a rock that maybe scores 60 is good rock, to answer your question in a simple way. Now, the issue of boring is neither here nor there. If you get good rock, if whether it's hard or not, that's a good rock. And if, as long as can be bored, of course, if it's sound rock and good and has no discontinuities and so on and so forth, boring will be expensive, but that's no issue, because it means to bore through it, the structure would be safe. So that's okay. The issue of hardness doesn't come in. The issue is the condition of the rock, and to say whether a rock is good or not depends on the only parameters we have are the classification systems that I think we are going to talk about in the future. So ideally, the exploration program should be developed with input from tunnel designer. It is essential to budget each phase properly, and budget for and make provisions for the entire geotechnical budget as a line item, and not something lumped into design. This actually allows greater control on the cost and cost effectiveness of the. Yeah, so actually, this I cannot stress this enough. Many people think that geotechnical part is a by the way. When they want to put up their structure, they say, I want to put a 10-story building. I have 50 or 40 or 60 million. They are looking for a structural engineer, and that's it. It's only the structural engineer sometimes that demands, okay, I need a geotechnical report. Comes as a, by the way, as a second thought. While in fact, the first port of call should be the geotechnical engineer, because this is important. And if, as if this is not enough, you can see buildings collapsing. I think Kajiado, I don't know, in Kangemi, in the city itself, and I think some parts away in Kenya. I think that has been a serious issue. And the biggest problem is this issue of not giving due importance to the geotechnical aspect. So then there's the need for geotechnical service to the life project life. That is true. You need to monitor, see if there are deformations, there are cracking. You need to if there's something needs to be done. Again, if the tunnel is well in service, works well in service, that should be a lesson. Should be well documented, so that in the future, as the principles used in the design of this project can be applied to other similar projects. So almost always, the sooner geotechnical information is obtained and evaluated, the greater the potential for optimization of the alignment and profile, and greater cost savings. The abundant geotechnical uncertainty requires tunnel exploration and designed to be iterative, The planning of the each exploration phase should be based on the results of the previous phase. Most importantly, the geotechnical exploration, including evaluation and report, must be available to the decision maker, so the design team in a timely manner. I think the report basically need to be available for people to make decisions, sound decisions. Ideally, just like for example, I give an example. I keep referring to the example of this even if you want to probably construct a house, the first because the you need information like, for example, the bearing capacity. This is can only be found from a geotechnical report. But you see, often people run to the structural engineer, but you need to size the foundations. How are you going to size if you don't know the bearing capacity? So the first port of call should be, so this is the point. The report, a geotechnical report, if available, gives the geotechnical engineer the power, or the makes him in a position, him or her, sorry, I would be accused of being a male chauvinist, gives him or her a chance to make a decision. Or without the report, then you cannot make a decision. Then you can say, okay, you go to a geotechnical engineer and look for a report. So this is what we are saying. So when the report is available, it aids in good decision making. So ideally, the phases should follow in immediate succession or overlap just slightly, so as to maintain uniform geotechnical staffing levels. You can see the level of engagement required in all these stages. So you cannot afford doing so many things at the same time. So you should phase properly. That when one phase ends, the phase of construction, then maintenance, for example, or monitoring. But if you try to is it called cascade, do so many things at the same time, then there's the likely chance that first there's this you can see this there's only people who are specialized. There could be issues with the staff level. They might be spread too thin, and when people are spread too thin, the likelihood of making mistakes are a lot. So you need to just a portion, or make the workload just enough for a certain phase, and then move to the next phase with enough staff level. Unfortunately, this is always not possible when the public work is done by a multidisciplinary team on a fast track projects, because actually most of the projects are by the government, or by private entities. They want results fast, so the phases may overlap or require concurrent work, in which case you need to beef up the human resource. The problem again is that this human resource, the specialties may be very limited. In fact, if you check even from the university, let's say, even the people who teach, you find that it's very the specialties, there are only very few people who specialize in a certain area. So again, you need to make a good use of these resources. And because the human resources, the people who are experienced, who have the capacity, may not be available enough for you to do so many things. What we are saying here, that when the when the work needs to be fast tracked, then many people need to do many things at the same time. So you need a lot of people who are specialized, many engineers. But if you don't have then as many as what you need, there's a problem. So this is why we say may not overlap like this. But in reality, when the projects are required in a hurry, again, you might need to have accelerated schedules. And in fact, this is the precisely the reason why you find most engineers, you can tell by probably the ones who teach you, are very busy. They are rarely found because you would work here, work here, because a lot of things are needed to be done. But the people who are specialists who can do this are rarely found. So you find one person doing this and that and that and so on and so forth. So on some projects, there are large gaps between phases. The geotechnical team must be disbanded and reassembled, or a new team must be acquainted with the details of previous phases. Both scenarios introduce drastic inefficiency, the potential for at least a temporarily misinterpreting data. Whenever large gaps between phases are anticipated, the geotechnical team should budget for. So we are saying again, you don't, because if for example, let's say the SGR, for example, the way it started from Mombasa to Nairobi, it's always a good thing to maintain the same group of people who are familiar with the data, familiar with the alignment. So you can imagine if you started in Mombasa and reached Mali, and for some reason you have to look for other people, the people who started from Mombasa. It's very easy for these new people to misinterpret something or misunderstand something or mistake something. So those people who started is easier because this consistency is in understanding and consistency with the persons that were involved from the start. So this kind of interruption is not is the issue. It's not encouraged. The geotechnical team should be budget for and then write a detailed report that summarizes the status and the significance of the data at the time of preparation, in case different personnel are assigned to geotechnical team. So this is just to learn to communicate as well, such that all these things are and counts and espoused in a report, such that in the unfortunate event that the teams have to change, then there is no room for misunderstanding. Okay, so the report needs to have enough detail for the next team. So again, collect and organize a phase. I think I need to finish. We won't take a break. We need to finish. So collect and organize phase. Spending the proper amount of time on this phase is the first step. Yes. So each phase you have to uh, allow enough time. If it's the phase for investigation, the phase for design, the phase for implementation, so that you don't allow time for mistakes. You can see that if things are done in a hurry, mostly the likelihood of making a mistake is very high. So each phase you need to give enough time so that things are done properly. So spending the proper amount of time on this phase is the first step to cost-effective investigation. Before any time is spent in the field, they publish information about the geology, soils, grounds. So this is just to say that first you need to spend some time. If you're going to do the investigation, you need to know where the site is in the first. You need to have an idea of what kind of, so go to it's a government project, go to the government bureaus where you can get data, the data for rainfall, get data for ground, whatever you can get, so that you have an idea. Also need to identify what kind of data are you going to collect, because you might reach the field and then again you don't know. After you spend probably you are consulting in Nairobi, you go to Wajir or Mombasa or wherever the project is, you spend money, then you're on site and you don't know what kind of information you need to collect. Also look for other similar projects to give you an idea, like, okay, what kind of data do I need to collect? So seismic history and performance of structures in the project should be collected, organized. I think it's just the same thing I'm saying. If there is data related to the particular area that you are doing the investigation, you can look at them as well. In urban areas, the history of the site is also important because it can identify old landfills. Again, is important. The You need to keep off landfills because these are or if you have to put a project in the landfill, you need to be aware, and because these places have issues of potential settlements, a lot of geotechnical issues. So if you're aware, then you're able to find mitigative ways. So geological and soil maps are especially, so the maps, again, the maps can only be I think in Kenya, government, maybe the Institute of Surveyors, I believe maybe the special engineers can help you with that, or indeed any government institution where you can get all this data you need. So a list of various sources of geotechnical data that might be available is shown. So this the table shown there gives you an idea of how, of the geotechnical information you might need to collect. So then the regional site recognizes, of course, you have to visit the site first. Reconnaissance should cover both immediate site as well as much larger area so that the regional geologic and hydrologic trends can be determined or verified. Geomorphological or geological interpretation of landforms in an area often reveal data that points to a particular geology or adverse geological features that will influence the type and amount of exploration that should be conducted. It is seldom possible to explore to thoroughly explore channel alignment directly during the reconnaissance phase. The geologic conditions predicted along the alignment are based on detailed knowledge of selected areas connected by interpretive skills of the engineering geologists. These essential interpretations are based on knowledge of the soil. The point is the you can only sample a few places and the rest you interpolate, but the interpolation requires some experience, some good insight. You just don't do a blind interpretation because it's impossible to, by the time in fact you're doing the alignment, because the tunnel will be underground, but how can you can only investigate from the ground, so you can see there's a limitation already. So that means along the where you expect the alignment, you can only dig limited pits to see, but in between, because the only thing you can be sure is for the observed place, the place where you have dug the borrow pit. Between the point you have dug a borrow pit and not borrow pit, sorry, on an observation pit to the next one, these distances you can only interpolate what might be in between, based, of course, on the data you've observed. But that also requires a skill, and so based on the knowledge of the soil and rock types. They are macro and macroscopic, mineralogic and structural features, geomorphic situation, and agents at work. Geological reconnaissance includes such of available literature, of course, the study of aerial photographs and satellite imagery. So you can see the challenge I'm talking about. All these things you're doing from the ground, the literature is available data, but the photographs, the satellite imagery, you can only do from above the ground, while in fact your tunnel is going to go deep inside the soil. So you can already see the challenge. In developing an investigation program, it should be remembered that the answer to some geological questions are not always found at work site. Relationships between rock units or structural features that are obscured at the work site may be obvious from some distance away. Aerial photographs are particularly helpful in geomorphic analysis and in evaluating the best alignment in choosing or evaluating portal locations. A considerable insight into engineering properties of rocks. is available. I mean, considering insight into the engineering properties of rock is available from the skilled evaluation of rocks response to natural testing. So I've said this, even when you take the samples to test, you can only be sure of the a few places you've tested, but then to know the rest of the behavior needs some skilled evaluation and interpolative skills. Now, feasibility and corridor study site investigations. The feasibility study must develop enough reliable information to determine technical feasibility and provide reasonable cost. Yes, this is important as well, because the tunnel projects as you already imagine, are cost if cost I would say cost are expensive, so to speak. What did I say? Cost intensive. This is the word I was looking for. Now, unfortunately, in this country of ours, sometimes you hear project and then something happens, and when the project is already, or some money is lost, they say the project was not feasible. So many problems. In fact, even you remember, a lot of questions have been raised about the SGR. But these are things, because when you're going to spend that amount of money, you must do a a feasibility study to make sure that this project is feasible, because you're using a huge, humongous amount of resources, especially if it's from the taxpayers. So, in a good, a good accountable system, then the first feasibility study accompanied with data. So you don't just say that this decision was. The decision must be accompanied by evidence, or reasonable data that, of course, this decision was made on this, and so to also make sure that the financial resources are used reasonably or economically well. So, reasonable and provide reasonable cost estimates to determine financial feasibility, and frequently to compare alternative route alignments. Actual boring and test pits are desirable and are frequently required to provide sound basis of cost estimates. And nothing will be more valuable for a tunnel corridor study than relevant, reliable, up-to-date geology and good quality up-to-date aerial photo coverage for corridor studies. General classical geological exploration with special emphasis on engineering geology feature is invaluable. So of course, you guys are in fifth year. This is a second year. So you did your technical engineering and you did geophysical methods. The ground penetration radar, the mass, MASW, those things you did them. So these indirect methods you can use, can complement. But please note, these geophysical methods may not replace the actual pits. All right. So they can help you interpret the data. They can supplement, but cannot replace the fact that you actually need to do a pit. And if you need to also to do an audit, an audit. An audit is a horizontal pit. So pit is vertical down, an audit is horizontal, and that's an examination question, a potential examination question. What's the difference between an audit and a pit? So features such as stratigraphy, fault zones, landslide hazard areas for portal evaluation, and ground information such as aquifer, aquiclude identification, location of springs, seasonal variation of springs are geological items of great significance to tunnels. For urban projects, the identification of significant man-made features is also essential. Particularly, attention must be given to existing sewer lines or other buried obstacles that any future tunnel must pass over. I think this already said, or beneath piles for fire structures and any potential hazardous waste. I've already talked about the nuclear. Geological maps should be augmented by actual geological inspection by qualified engineering geologist who is well versed with the engineering and geological needs and sensitivities of the tunnel to advise. So the idea is, even if you have the maps, because the while the maps are useful, they give you good insight and so on and so forth. But I'm sure you know that you have seen some maps that even maps of your own village that do not really represent what is in your village. So these things have been made by humans. So as much as they give a good first a good overall overview or a good impression, so that you can have a good general idea. However, the details, now when it comes to the details, sometimes the details may be misrepresented or not well represented. So when you have the map is a good guide, yes, but you need to go to the ground and see whether what is in the map coincides exactly with what is in the ground. And in countries like ours, where there's a lot of issues, land grabbing, so many things change. So it might show that there's a government thing here, or a sewer line here, but probably someone already grabbed, and things have changed. So these are things that you need to uh, to 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 think about. So geological features, tunnels to advance geological features. This should be done personally by an experienced engineering geologist or geological engineer who walks the corridor or spends a considerable amount of time in the country ground of corridor at the appropriate location. Long corridors may be more amenable to geological helicopters. So if you can get a helicopter and it's a long stretch and you have the money, I think it's better, because you need to get as much information as you can, which can land whenever desired. So again, it's not only a good thing to fly above the air. So sometimes when you're required to land to see, because the from the air gives you the advantage that you can do a wide area in a short time, but also it's possible that what you're seeing may not be actually what is in the ground. So when you need to land, even though you are on a helicopter, you can do to check to confirm whatever it is that you're seeing from the above. So engineering geologists who are well versed with engineering and geological needs and sensitivities of the tunnels to adverse geological features. This should be done personally by an experienced so they cannot be proxy. So the experienced person need to go to the field to see, or geological engineer who walks the corridor or spends considerable amount of time on the ground of the corridor and the appropriate locations. Yeah. So the experienced person need to go in person to see, to check the salient features, the most important things, the stratigraphy, if you can examine the soil, the kind of rock, the nature, the jointing, and so on. So long corridors may be more amenable to geological. I think we said this. Is this a repeat? No. Okay. However, it's essential that considerable verification of geology on the ground be I think I've said this, that it's important. Whatever you see on a map or on a helicopter, you need to go and see, confirm that it's actually what you see is representing the reality. So preliminary site investigation, a substantial portion of geotechnical effort that goes into a project is expected during preliminary design to gather the information and conduct analysis needed to support preliminary engineering design. Alignments may change as a result or reverse geology discovered during preliminary investigation, possibly leading to additional exploration needs. So basically, the preliminary investigation would help you to flag red to maybe let's say red flags, so to speak. For example, if you find that the initial planned route there is a hazard, a hazardous waste, for example, or there is a fault, the fault may be fault to a limited extent such that you can avoid it altogether. So not because the previous example that I gave was the Rift Valley, like in Kenya, is extends, I think, the entire length of Kenya. So if you want to go to the east, to the west, you cannot avoid it, for example. But if there is a valley, a Rift Valley, only to the northern or the southern part, so if you realize there's a fault line somewhere and you can find an alternative, I think that's the safer way. So preliminary investigation will help you to to flag off these issues to and you find a solution. So the final design, this is comprehensive exploration that is planned to fill the gaps between the preliminary design borings and to confirm earlier geotechnical assumptions. Now here you, because during the preliminary investigation you've checked the maps, you've done, and you've made, you have an idea of the kind of rocks, the kind of of of, um, of jointing, the nature, and so on. So from literature, from what is written, now you go to the site to see for yourself whether these are actually true or not. And then even as you do this on site, you have to write a report. Now here, a detailed borehole logging, uh, as you and as you take in the data. The exploration program may include pump tests, in situ tests, exploratory shafts, adits. Adits I already talked about, adits or pilot tunnels, and other large-scale tests. This phase also includes confirmation of geologic profiles and engineering design parameters, analysis, detailed geotechnical evaluation of geotechnical conditions, and anticipated behavior and preparation of reports. So in this case, you collect for these days. I think it's unfortunate in our places we don't invest a lot in computer programming. The world these days, a lot of numerical programs to help you, because you can see the complexity in all this. So we don't rely so much on in the current world. We don't rely so much on manual calculation, but we rely on numerical analysis. But also not numerical analysis only, of course, coupled with proper knowledge. For example, here you have to know, you have to, the input parameters, for example, in the software have to be properly determined here. So for example, you need Young's modulus, Poisson's ratio, the stress strain curves, a lot of things. The input to the you need maybe the most basic, you need the self weight. All these things have to be thoroughly evaluated. So the final cost and data investigation, there is often a need for additional exploration after the major final decision have been made. This is intended to fill any gaps from the final design exploration, with special emphasis on obtaining data, the data estimators, and help contractors need to make reliable cost estimate. This step has not normally been formally identified in the past, but should be in the future. Yeah, because after you do all that, you investigate, you find the project is feasible, then and before, because you know this is not this a lot of money required, a lot of safety concerns. So there's the final part before now doing the construction. Someone needs to go on site to check to be sure, to verify all this, to get additional information. In fact, actually, in the report before this, the final report, of course, there are gaps that have been identified. So you go back to the site to actually see the gaps, to fill the gaps that was missed in the previous case. And most importantly is to cement your position that the conclusions or the results from the previous study, just to be sure that okay, this can stand, and get more reliable information for a reliable cost estimate. So the construction and post-construction investigations. Investigation continues as the ground is exposed and its behavior observed and measured. So even during the no, you don't stop that. Okay, that we had done in-site investigation, we've written report, we've done a geotechnical drilling program, so that's enough. So even during the construction, you keep monitoring, and if you see anything strange, depending on the hierarchy of the project, you take note and write a detailed report to see. So this is this is also a way to you can see, you can notice if something strange is happening, and this also is a way to avert danger. As you can, despite the fact that you have done a lot of investigation, you have a pretty good idea or some good information on the site, but still the whatever cannot be predicted accurately is a lot. So still, even when you're doing the project, your eyes still need to be out there to see what happens. So you need to train. They always blame us engineers that we don't know how to communicate, or we are not taught to communicate properly. Again, here you need to learn to train the teamwork, communicate properly. Um, this is I like to watch this some it's called pilot. There's a pilot show I like to watch on YouTube. Uh, it shows the program shows you if probably if a plane crashed and why, tries to investigate. You give some insight on the possible reason, and often you realize that okay, let's see, if you the plane should have, okay, I am no specialist here, but based on what I have watched, that mostly we have, okay, we can have at least two pilots to fly, but depends on the distance. You can have more pilots. The first pilot is the captain, the one who is actively steering the plane, in putting the controls and so. Now there's what you call a monitoring pilot on the side, or side by side, but the one with the controls is called the captain. So you might also have a flight engineer, and or called a first officer, or yeah, so can have four or three, or at least two. The reason for all this is because if there is an incapacitation and so many things, so the plane, someone if someone is incapacitated, someone can take and steer the plane. That's the first reason. The second is during landing and takeoff. There's a lot to do, So probably it's better when it is done by two people. But again, you can see when two people are doing the same thing, because the aim is to make sure the plane gets off or the plane lands. So despite the fact that you are two people, you are steering the same thing. Again, then communication is important. So in most of the cases that the plane crashes, you notice that there is a miscommunication between the people involved, either the first officer and the monitoring pilot, the captain and the first officer, or captain and the monitoring pilot, or the monitoring pilot and the captain. So miscommunication, as you find sometimes you the because the function of the first officer is to check what the captain is doing, and if he doesn't agree or thinks that is jeopardizing the safety, should suggest suggest a corrective measure. So the point here is about communication. So sometimes crashes happen because the one person has notified that there's danger and is trying to communicate to the other person, but either the communication is not effective or they end up misunderstanding each other, and then the planes crash in most cases. Sometimes there is also a good ending, that due to effective communication, the plane does not crash as doesn't crash, and the plane gets home safely. Anyway, the points of for communication. So the same idea, I'll use the analogy of the plane. Everyone involved is like a pilot and co-pilot, and proper communication. Otherwise, if you don't communicate properly, a disaster might happen. People might lose lives or even lose money. So underground projects involve a number of technical specialties. The common thread is the geology and its geotechnical aspects as ascertained by the geotechnical investigations. Geotechnical results and their significance must be understood and used properly by the entire team, not just the geotechnical engineer. So everyone involved have to understand, because you are doing geotechnical. Geotechnical engineer is a specialist with the soil, but still he needs to communicate effectively to the other people. For example, the one who will design the bolt, the most likely stuck. But anyway, it's difficult to make a distinction. But bolts probably structural engineer, but who need to know some geotechnical knowledge. For example, you need to know the strength of the rock. For example, how much are you going to design the tensile strength? The same idea analogy I was giving you before. A structural engineer and a geotechnical engineer. For the geotechnical engineer must write a report to tell the structural engineer this is the bearing capacity of the soil. So it is the same idea. So the geotechnical engineer has to work in tandem with these other people, these other persons, and the report has to be understood, and there's no room to misunderstand. And of course, there should also be a line that if and then someone doesn't understand a thing, they can consult so that the clarity is sought. Each specialist must understand the concerns of the other team members, their special needs, and how his work impacts the others, and vice versa. More information rather than less should be transmitted, and lack of need to know should never be presumed. Yes, so you cannot say here this idea that if you have data, someone should not see. This is my no. This is for all of you, and you everyone has a blind spot. So you may think the data is saying this, you show the other one might see something else in the data, something insightful that might be useful. So you cannot say that this is your data, you don't show anyone. The anyone, people have this. If you go to where people work, some people think that this is ours, those are other people. So when you have something you don't share, you show, because all these people to have something unique to contribute in this team. So, and they have They are here because of their own areas of specialty. So you need to check each can have a good insight that will be useful to the project. In any case, the aim of everyone is to contribute to the project, and not people to each individual to monopolize to monopolize. So, and then the geotechnical and geological specialists, because tunnel projects are geotechnically intensive, a well-trained geotechnical engineer, geological engineer, or geoengineering geologist must conduct the exploration and evaluation. This geospecialist should be well versed in tunneling and should have spent significant time actually underground during construction. Drilling tests, pit, and other exploration subcontractors, it is essential that the project manager of the drilling company, as well as the driller and driller's helper, understand the special needs of your project. This will require face to face briefings every time a new project or phase starts, supplementary by frequent reminders in the field in particular. So, for this kind of projects, we cannot afford this kind of online meeting. Is better face to face, in person, the first hand experience, so that you understand the because there's a way this the online thing takes the first hand experience. So when you're on site and you see things in actuality, then it's more real. So precise knowledge of the depth at which geological units are encountered is essential in tunnel projects, because the actual strata changes will be exposed in the tunnel's excavation. When drilling 100 feet deep boring for building foundation, it may not matter whether given certain changes at say 79 or 81 feet. However, if the crown of the tunnel is planned to be at 80 feet, it is important to know whether a change occurs at 79, 80, or 81 feet. It is also important to tell the driller whether you wish to excavate as fast as you can, or if you are more interested in making sure you are not missing vital information. This requires special briefing to the driller as well as care in preparing the drilling contract. It is possible to make a hybrid contract where the driller is on footage basis with special provisions for hourly payment all this. So as a design engineer, you need, because you're not working in isolation, you'll work with other people. So the drillers, you'll need to employ someone else. So all this is important. So when the geotechnical team needs to go slower to improve quality of data, the driller should be also be briefed on the purpose of the boring, field test, and on the type of information being sought. Groundwater information, e.g., first encounter of groundwater, any carving of holes, changes in drilling behavior or cuttings, etc., is particularly important, and the driller should know of the extreme importance of such observation. This briefing should be repeated frequently in the field. So to the designer, now this is a specialist. It is important for the designer and the technical staff to be well versed in each other's concerns and issues. The designer must understand the risk associated with the limitations of geological interpretations, as well as the technical issues. Most geotechnical data is extrapolated rather. So this is actually a very real thing even for the design of foundations. The data we get is very is you need to be careful. Is interpolated rather than so. For example, they give you my experience with the foundations in Nairobi for the projects I've been able to write a report. You dig, you find maybe the topsoil is clay or red coffee soil. Then you dig. Luckily, if you get rock, now once you get the rock, you cannot stop and say, okay, fine, because in any case, actually, you need the best foundation you can find is rock. That's the first thing. Now, when you find rock, first you need to check, is this rock continuous? Because otherwise you can find rock and then at 1 meter, then you go to 5 meters, you find another soil. So the first thing you need to ensure this rock is not is continuous, is not as an isolated patch of. So if you write a report based on the fact that you've just hit rock at 1 meter, then the information is bound to be missing. So you need, in fact, you need to do a pit for up to maybe 10, depending on the if you are doing 8 story, 8 story is about 3 times 8 is 24 meters. You need to do at least half the depth of the now this is good info. Okay, this is also useful for you for your experience. Anyway, for 8 story, you need to do at least half the height if the ground is good. If the ground is poor, you need to do this almost the same height of the building. But this is expensive. The you tell the owner and you may not agree with you. It's gonna be very expensive. So this is just to show you the information interpolated. So in which case, once you've seen that there is rock, and probably you cannot continue to do the investigation based on the amount the client is willing to pay, then you have to find measures in just in case this rock is not continuous. You have to think of ways to take if you recommend to them, for example, because of course at the end of the day you're still responsible for the report you write. So if you cannot be able to continue digging to the depth that is required, and then you're lucky to find rock, you note that, but you have to give them a recommendation to make sure, just in case this rock is not continuous to the required height, then what can be done. This was the idea. So this is where experience comes in. And now I've given you an example with the basic, subsurface foundation. Now you can think of how much more complicated in the tunnel, where you don't see anything, but you use just isolated data. So, but this is the idea. So, and then the owner again, of course, the owner is usually not a specialist. You are the specialist, the designer, the contractor, and all this. The owner is a person who wants the project implemented, but mostly they have no idea even what is happening. But they have a legal responsibility as well to pay the client, the contractor. They have a legal responsibility to hire qualified people, because if they hire you probably as a specialist, and you need another a specialist driller, and he doesn't want to pay the money. So there's some legal responsibility that he has. So then he also has to be involved. So the owner and its legal staff must also be aware of uncertainty and the impressions of. So he might hire you that you're a specialist, you are a genius, for example, and then don't tell him that whatever you're going to the result or the report you're going to write is cast in stone. No, he has to know that we use science to try to predict the behavior. The science is reliable when interpolated within certain boundaries, but he needs to be aware that there are some uncertainties that no amount of science, or even if you are a rocket scientist, you cannot. So even the science can help us, but only within certain boundaries. Of course, if applied properly, the project will be. Because otherwise, if he thinks you're a genius, and maybe it's called tooted your horn too much, and then when you get the report is different from what you expected, you might start arguing over money and lawsuits. So you need to be aware that science can only do so much. Experience is important, and so on. So, and then on the result, so these uncertainties may only result in larger geotechnical budgets. They need to be aware that most tunnel owners might expect. They also create the need for special types of specifications and risk sharings, contract provisions. Legal staff must be aware and trained in all the new changes in contract practices, such as different site conditions, full disclosure disputes, the review board, geotechnical design summary report, in contract documents, etc. And now, actually, the FIDIC, I don't know, you guys, I think you should have learned FIDIC. This is a special condition that provides ways to resolve disputes, because these kind of projects are quite specialized, and in a court of law, if you try to canvass these issues, even the lawyers have no idea which any of you are talking. So we have special, it's called dispute resolution boards, that have these specialists that might understand whatever you people are talking about. So again, the owner has to know all these things, so in case of any dispute, you guys can find your issues solved amicably. What was this thing? The role of geotechnical uncertainties in the development of these legal trends should be well understood by the owner and its legal staff. Construction parties, Uh, the tunneling contractor will already be painfully aware of the hazards associated with the geotechnical predictions. Nevertheless, it is important to be realistic about what can be predicted reliably and to be constantly on the lookout for unexpected conditions that need changes in construction methods or may merit filing of a change condition claim. The construction manager gets essential data from the contract documents. So all these things, even this why we are saying the owner needs to be aware, because once there was a contract price, he needs to know that if there are certain drastic conditions encountered during the construction, then the contractor has a legal right based on FIDIC. I think you guys have the example of FIDIC, conditions of contract. The parties, the contractor has a legal right to vary, to claim, to uh, submit additional claim without prejudice to the owner, to the owner. And they need to be aware, because otherwise, if they are not aware, then when such issues arise, there's bound to be conflict. The construction manager gets essential data from the contract documents, especially the what is this design, something design report, geotechnical design, something report. Let's see, GDSR in a geotechnical design summary report, and final geotechnical report. The the construction manager should be highly experienced in underground construction and should be thoroughly briefed on the important geotechnical requirements and uncertainties anticipated in each particular project. Government agencies and their legal staffs must be aware of uncertainties and imprecision of geotechnical predictions, especially if the design must be reviewed and approved by a third party and giving easement to the project. Finally, construction parties, training for everyone involved in a tunnel project is absolutely essential. With proper training, team members can perform a wide variety of tasks if given the opportunity. At the minimum, some clients owners may be oriented to the uncertainties. In particular, it is essential that the important geotechnical aspects of the project be clear to all staff. As a result of the training, which should be broad and conducted frequently. So that's our class. Unless there's a question, class rep, wait. Yes, yes. You go home.